All right, so this is the second video for chapter 9, covering section 9.2. So please pause, copy this panel, and then press play. All right, so in this panel, we discovered that there's a problem with covariance that we are not happy about, and that causes us to create a solution called correlation coefficient. So what's the problem? Let's suppose we have two random variables, x and y, and their measurements. Let's say they're measured in inches. So maybe it's somebody's height versus their girth, the distance around their middle, something like that, right? And let's suppose we've got a bunch of data and we've calculated the covariance between x and y to be 0.8. Now, my buddies in Europe, they don't understand inches. So I'm like, oh, okay, well, I'll just convert to centimeters and okay, off we go. But then a problem arises. So to convert into centimeters, I multiply inches by 2.54. So I multiply x and y by 2.54. And I go to test my check my covariance or compute my covariance. And all right, well, let's see what happens. So there's my covariance, my two random variables in centimeters. There's the very definition of it. It's the expected value of the product of the two random variables minus the product of the expected values. Expected values love to have constants dragged out, constant multiples dragged out. So both 2.54s can come out of that first guy, and then 2.54 can come out of the first e of xy, 2.54 out of the second e of xy, and I get another 2.54 squared. So look, there's 2.54 squareds in both spots. I can factor it out. E of x is mu x, ey is mu y. So, oh my gosh, that's the covariance of x and y right there, but it's multiplied by 2.54 squared. So my European buddies don't think the covariance between these two random variables is 0.8. They think it's 0.8 times 2.54 squared, which is, I don't know, 5-ish, 6-ish, 7-ish, I don't know, some number like that, but definitely not 0.8. We don't like that, right? So just because we change the unit of measurement, we don't want this sense of how linear and what kind of slope we have between the two random variables. We don't want that sense to change, okay? So we got to fix it. All right, so here's the fix. So why don't you pause, copy it down. You'll notice no green ink, and then press play, and we'll keep going through it. Okay, so the fix is going to be to somehow standardize the scale, right, of the covariance. And we're going to call it the correlation coefficient. It's denoted this sort of slanty p, which is the Greek letter rho. So we're going to call rho of xy the correlation coefficient. And what we're going to do is we're going to take the covariance and we're going to divide by the standard deviation of x times the standard deviation of y. So we're going to, in some sense, standardize the covariance by dividing by that thing, okay? All right, and we get a really nice proposition here that's going to solve the problem for the previous panel. Proposition says if I take a linear function of x and a linear function of y, it doesn't impact the correlation coefficient. So the correlation coefficient of x and y is the same as the correlation coefficient of a plus bx times c plus by. Okay. Now in the last panel, I just had a b times x and a d times y. I didn't have the linear term added, but this will show more than just the problem we had in the last panel. All right. So how do we prove it? Well, I'm going to start with the correlation coefficient of a plus bx and c plus by. And there's the very definition of it. It's the covariance of those two linear combos divided by the standard deviation of each of those linear combos. Okay. And then a homework problem occurs. And poof, eventually, the A's, the B's, the C's, and the D's have all disappeared. And we've got the correlation coefficient of just x and y. Okay. This should not come as a surprise, right? Adding a constant to your variable doesn't change the variance, it just shifts the data up. All right. So this shouldn't be a shocker. There's definitely some homework to do in here, but I believe in you. All right, so I'm going to leave that to you folks. But that then shows us that my European colleagues' correlation coefficient is the same as my correlation coefficient, which makes me happy. Okay. So what this proposition is showing us is that rather than using just x and y, I could always use the standardized version of x and y. And you've seen standardized versions of random variables before. When we do normal random variables, when we standardize them, what we do is we take the variable, we subtract its mean, and we divide by its standard deviation. That creates a new random variable that has a mean of 0 and a variance of 1. If you remember from our normal table, we always like to get to that N01 situation. So the correlation coefficient don't care whether you use X and Y or the standardized version of X and the standardized version of Y. It'll give you the same exact correlation coefficient, right? And what's nice about this is if we look at the correlation coefficient of the standardized versions, I can throw the definition of rho at it. And if you remember, the variance of a standardized variable is just 1. So the standard deviation is just 1 as well. So the denominator is just 1 times 1. I just get the covariance of the standardized versions. Okay. So I can either do the correlation coefficient of the original random variables X and Y, or I can do the covariance of the standardized variables X minus mu of X divided by sigma X, comma Y minus mu of Y divided by sigma Y. Okay, so let's look at a couple of properties or propositions about the correlation coefficient, and then sort of look at how do we apply it to actual data, all right? So here's the first one that says, no matter what X and Y are, the absolute value of the correlation coefficient is always less than or equal to 1, okay? All right, so let's prove this. Well, first off, let's get the standardized version of X and call it Z sub X, and the standardized version of Y and call it Z sub Y. Now, X and Y, maybe they're normal random variables, maybe they're not, maybe one is, maybe one isn't, I don't care. But if I do this standardizing process, Z of X has mean of 0 and standard deviation of 1 and variance of 1. Okay, same with Z of Y, right? Just because I've subtracted the mean and divided by the standard deviation. Go calculate the expected value and the variance of that. You'll see it's 0 and 1. Okay. All right, well, let's see here. Let's take Z of X and either add or subtract Z of Y. Don't care which one, and calculate the variance. Now, variance is always greater than 0, okay? So that's how I get that greater than or equal to 0. The variance of any random variable W is always greater than or equal to 0. I mean, it's the expected value of W minus its mean quantity squared. So it's the expected value of something that's 0 or larger. So it's going to be 0 or larger. Okay, by work from the previous video, I can split this thing into the variance of Z of X plus the variance of Z of Y, and then either add or subtract twice the covariance of ZX and ZY, because that subtraction sign just get dragged, right? No worries there. Now the variance of Z of X is 1. It's a standardized variable. Variance of Z of Y is 1. It's been standardized. And then the covariance of the standardized variable of X and the standardized variable of Y, well, we know that's the correlation coefficient of X and Y from the previous panel we just talked about. So I get this equation. So the upshot is 0 is less than or equal to 1 plus 1, which is 2, plus or minus 2 times the correlation coefficient. And then if I subtract the 2 to the other side, divide both sides by 2, I get that bad boy. So I get that -1 is less than or equal to either the positive or the negative of rho. Well, the only way that can happen is if rho's absolute value was less than 1 to begin with, okay? Because -1 is not less than or equal to -2. So rho of X cannot possibly be 2, right? So it's got to stay between -1 and +1. So the absolute value of rho has to be between the absolute value of rho has to be less than or equal to 1, okay? Or in other words, the correlation coefficient of any two random variables is always between 1 and -1. Maybe 0, maybe 0.9, whatever. All right, then we got this really cool result. So pause, copy, play. All right, now this one's really cool. So this proposition or property about correlation coefficient says that if your absolute value is 1, that happens if and only if there's a linear relationship between Y and X. Not just like Y is almost linear in terms of X. No. Y is a linear function of X. They are utterly dependent upon each other in a linear relationship. It's huge for some real numbers A and B. Okay. All right, this we got to prove. It's an if and only if. So that's telling me if I know this first statement, then I know the second statement is true. Or if I know the second statement is true, then I can for sure know the first statement is true. Right? So I got to prove two different things. So I'm going to prove what we say is the forward direction. I'm going to assume the correlation coefficient is, without loss of generality, I'm going to assume it's 1. The other argument would say, well, what if it's -1? And it'll work very similarly. Okay, trust me. Let's just assume the correlation coefficient is 1. Now, via the previous proof, I'm going to jump to this variance of zx minus zy that we set up. And we had 1 + 1 - 2 times the correlation coefficient of x and y. So I'm grabbing the negative, the subtraction case, and the subtraction case in the previous proof. I've assumed the correlation coefficient is 1, so I'll replace that in there. And look, I get 0. Okay. If I had assumed correlation coefficient was -1, I would have used the plus case in here. Okay. Either way, I've now shown that the variance of zx minus zy is 0. The only way the variance of a random variable is 0 is if that random variable is always a constant. Otherwise, there's going to be variance, right? So zx minus zy has to be a constant. And now I can just do some algebra. And I think I've, tweaked the, maybe I've misused the notation here. Maybe that's a plus now. I don't know. But it doesn't matter, right? I can solve for zy, and I get zy is equal to like maybe -zx plus c. Doesn't much matter, right? I can take zy, replace it with y minus mu of y over sigma y, zx replace it with x minus mu of x over sigma x. And if you note, I can take this monstrosity, mu, sigma, c, these are all constants, so I can just do some algebra and get it into this form, right? Hey, that's a linear function. That's what I was hoping to show. All right, let's go the other way. Let's assume I knew that y was a linear function of x. Well, if I want to calculate the correlation coefficient of x and y, I can say y is a plus bx, since I was told that. And I know from previous proposition that the a and the b doesn't affect the correlation coefficient at all. So I can just scrap them, and it's correlation of x and x, which by definition is this. The definition of the correlation coefficient. Covariance of x with itself is variance. And if I take variance divided by the square root of variance times the square root of variance, that gives me a 1. Okay. So that's kind of cool. I get that result. Now, with data, to distinguish sort of sample versus population, we often call this row that we've been looking at in these panels the population correlation. And in the next panel, we'll look at the sample correlation. Okay, so now we're going to move on to how do you deal with this idea of correlation with data. So why don't you pause, copy, and then play. All right. So how do we alter correlation coefficient to work with data? So let's say I have n data points, xi, yi. Then I have something called the sample correlation. And what I'm going to do is I'm going to do exactly what you would expect. So instead of the covariance, I'm going to have the sample covariance. And remember, sample we divide by n-1, not n, in order to be unbiased, right? So there's the numerator is my sample covariance. And the denominator, instead of the standard deviation, I'm going to have the sample deviation. So that's the square root of 1 over n-1 times the sum of xi minus the mean of the x's squared, same y's, okay? All right, now the algebraically happy amongst you will observe that I've got a root 1 over n-1 there. I've got a root 1 over n-1 there, multiplied together. I got a 1 over n-1 on top. So those all cancel. So I'm just left with the same expression without those n-1s and denominators, okay? Could have also put 1 over n's there instead. They still would have canceled. So then is what we call the sample correlation. Now, R, which only deals with data, simply calls this sample correlation the correlation. And we can calculate it using this core command, which I will show you next on R. Okay, so now I'm going to share the screen just to sort of show you the correlation command. So this is in the chapter 9 file, R with select homework. And I've clicked on sample data so it knows what I'm talking about. And so if I come over here to the top left, and I'm looking at lines 10 and 11. So in lines 10 and 11, I'm going to define x and y to be vectors, right? So the data points I have here are 1, 4, 0, 2, 4, 12, and 10, 23. So I'm going to run those two lines to tell R what x and y means. And then I can calculate the correlation coefficient of x, y. And I get a correlation coefficient of 0.996. And you'll note that's almost 1. So that's almost telling us that x and y are in a linear relationship to each other, okay? All right. I can also pull data in. So if you remember the spruce tree file, we have the change in diameter versus the change in height. And I can plot that, he says. And if you look in the bottom right, if you look at it, those data points appear to be kind of like there's a linear function that would fit them kind of well, and that linear function might have a positive slope. Well, we can calculate the correlation, and we get 0.902. So that 0.9 is telling us that the change in diameter is positively correlated with the change in height. So if you change the diameter by a positive amount, it's going to cause a positive amount of change in the height. A negative correlation would say kind of a negative slope. So if one quantity gets larger, the other gets smaller. This is not indicating that, which is also corresponding to what we're seeing in the plot. All right, I don't know what the second document is doing. Same thing. Okay, that's it for this video. That's the end of section 9.2.